Okay, we got another fun problem. This one's a slight twist on one we've done before. So let's go ahead and dive on in. So the statement is, how long does it take a falling circular ring, radius A, mass M, resistance R, to cross the bottom of a magnetic field B at its changing terminal velocity? All right, let's just kind of draw it out. So instead of a square loop, which we've seen before when it was in a magnetic field, we have a square loop. And we note that as it's passing at z-axis, it has some distance y that it's through. And since it's falling out of the field, we know that the distance that it falls out of the field is L/2. This will kind of make sense more in a second, but let's be aware that this is how it's oriented. And we'll see how that matters. So here, what we found for the solution previously is that we know that the net magnetic force on a loop was F equal IBL. I'll go ahead and reference the question for you so you can see it. But what we need to do is find I and L. Okay, so since V equals IR, we can find I from V over R. Here, the EMF will give us the V that we need, which is equal to the negative flux derivative, or the negative time derivative of the flux. Okay, we have some weird geometry here, so that flux integral will become very unique to deal with. All right, so let's go ahead and try to tackle this. This is easy. This is best done since we know that this is a symmetric configuration with respect to x. So let's just go ahead and multiply everything by 2 and deal with that accordingly. So that's where we get the 2b inside the brackets. Now what we want is from negative a to y. But what does negative a represent? Well, remember that the ring was radius a, and y was the distance of the field that's passed through it. So the difference there is what tells us what is still in the field. Okay, so negative a gives us that since it's on the left-hand side of the z-axis, and y is on the right-hand side. So that's what tells us what part of the ring is still in the field. Okay, and then of course, since this is a ring or a circle, we know that we can write the circle as x squared plus y squared equal r squared. And then if we solve this for y squared, we get a plus or minus square root. But instead of having a plus or minus, we abuse symmetry and just double it, hence the 2b and the positive root here. So again, this is a fun calculus problem, but be aware that things existed before this to help us with this. So if we go ahead and solve this integral, we get just a squared minus y squared, since the a squared minus a squared cancels out to 0. And then we take the derivative of it, and what we see is that we get dy dt. Again, this integral is not necessarily the easiest, but go ahead and use a table or convert it to polar if you want. There's several ways to do it. But anyway, since we have dy dt, that goes to negative v, okay, since it's opposing it. And then you see that we just have the negatives cancel, and we're left with 2bv over r, square root of a squared minus y squared. Okay, a lot of this is based on how you set up the initial geometry, so choose your poison wisely. It can go vertical if you want, but, set it up accordingly. Be smart about it. Now, what we also see here is that L/2 is equal to a squared minus y squared. If we go back to the drawing, the distance of L2 has to be equal to the height difference of the square root of a squared minus y squared. So we see that L is equal to 2 over the square root of a squared minus y squared. So based on the force equation that we found a long time ago, this is equal to 2bv r over the square root of a squared minus y squared times b times 2 square root of a squared minus y squared. So once we consolidate it all and simplify it, that leaves us with the force of 4b squared v over r times a squared minus y squared. Okay, and at terminal velocity, the force is balanced. So we're left with this force is equal to mg, where m is the mass of the ring. So solving that for v, we see that the v circle is equal to rmg over 4b squared, a squared minus y squared. Pretty easy algebra there, all things considered. All right, now to solve for time, recall that dy dt is equal to negative v, so dt is equal to negative dy over negative v. Again, separation of variables does this for you. And then, so integrating this, you go from t circle, which is at plus a to minus a, again, left to right. And then you get negative dy dv over dv, so the negatives cancel. So that negative sign allows you to flip the integral bounds. And just go ahead and plug in v that we found with respect to dy. Okay, clearly dividing by a fraction is the same as multiplying by the reciprocal. So, and then the 4b RMG is a constant, so we just pull it out. And we're left with a squared minus y squared dy. Again, pretty simple. This is a simple integral, so just plug it on through. You see we get 4/3 a cubed, and thus the time for the circle is equal to 16b squared a cubed over 3 RMG. Pretty fun, but definitely be aware that your geometry will make or break this problem.